Good day, class. So let's move on to the last part of module 5 and the module 6, which deals with welding. So the last part is basically the introduction to welding, and as I always say, our reference book is the Bible of Manufacturing, the Manufacturing Engineering and Technology from Kalpakjian and Schmidt. Again, you may also refer textbook by O.P. Khanna. Clear? So, welding is a common process. Some of you might have seen it, some of you might have done it. Well, it is a very important joining process which is present across the whole manufacturing spectrum, whether it be in a heavy fabrication area such as shipbuilding. You can see here a ship being constructed. Yeah, just a moment, let me switch on the pointer. Yeah, so you can see a ship bulkhead. Okay, these are called the bulkheads. Ships are manufactured in parts. Okay, these are all welded construction, and each part is joined together again by welding, and that's how a wall ship is produced or a wall ship is manufactured. Clear? So if it is shipping, or the most common thing or the most familiar one, building a bus body. So present day bus bodies are all metal parts or all metal joints. In the olden days, you could find more wood structures in a bus body, but the present day bus body is 99% metal, and that too a welded structure predominantly. And if you go into the micro side of manufacturing, so this is a part of a pistol. Okay, so you can see welding at a micro level, part of a pistol, and welding at a micro level. Still more there are still smaller things which can be seen with the application of welding. See, even a still smaller level. So these are some of the if you look around, you can see fabricated stuff. Anything which is manufactured by men are made of components, right? They almost all things right in front of your eyes, they are not able to be produced as a single unit. They are manufactured as individual parts, right? And these are manufactured as individual parts and assembled by joining techniques, right? So if you look at a knife, kitchen knife, so it has got different components: the blade and the handle joined by a mechanical fastening. Here it is, you can see it could be a riveted joint, right? Or an automobile, a car, which consists roughly around 15,000 parts, right? So it is again produced as individual parts and joined together. Okay, so if you move into the higher side, you can see a Boeing 747, a Mammoth, what do you say, aircraft. So it composed of 6 million components, right? 6 million components, and they are joined by different means, and welding is one of them. Then we have riveting, then we have plastic welding processes, right? So the joining processes are, some of the common joining processes are welding, brazing, soldering, adhesive bonding, and mechanical fastening. So the importance of joining process. Okay, why do we need to produce components and join together? Why can't we produce it as a single unit, right? So that's a common question that may come across your mind. The first point is it may not be economical, right? It may not be economical to produce as a single item, right? So if you imagine a table lamp right in front of your table, if you have determined to produce it as a single unit, it may take extensive or very complex engineering to make a mold to produce a table lamp. But if you produce it by producing different components and joining it together, it will be more economical, the task will be much more simple, and the product will have much more functionality and aesthetics. Yeah. So why do we need to produce parts and components? Because one point is parts need maintenance, right? See, if this suspension system of an automobile is produced as a single part, the dismantling and assembly and reassembly will be very tough, which affects the maintenance of the part. Clear? Another reason is that different properties may be incorporated into a single component, a single machine or a tool, okay, for the functional purpose. See this cutting tool, which has a carbon tipped end, right? It has a carbon tip. These two are two different material. This is one kind of steel, but this is a carbon tipped material, which is very costly compared to the shank of the cutting tool, right? So what is the advantage here? You can see here the advantage is that you may use a very small amount of the costlier material compared to the affordable material. So it's a huge cost saving in that, just because you could produce it as different components and joining together. Transporting components to work spot and assembling. Okay, so that is another issue. That is another factor in producing a product as different components. See, bicycle, different components are manufactured at different sites, and they are brought together at a single site and joined together, which is much more economical. Welding, as we have seen, welding is faster than riveting. You might know what is riveting, right? Okay, and then it gives a stronger and a leak-proof joint compared to riveting, right? Or bolting. It may give a stronger and leak-proof joint. It is more economical. Why? Because it has got less components compared to riveting or compared to other fastening like nut and bolt. It is more economical because less parts, right? Can join dissimilar metals. Well, you can join dissimilar metals, but in the olden days it was not possible to join dissimilar metals. But the present day technologies allows the joining of dissimilar metals which has different properties which may not normally fuse together. The advantage is gives a better surface, right? If you go for riveting or if you go for nut and bolt, it may not get a uniform surface, but if you go for welding, it may give a better surface, and it gives flexibility in making process changes. It's highly flexible. Welding is highly flexible, but if you go riveting and all, it has got many restrictions. If you go for riveting or nut and bolts, it has got many constraints, right? Applications of welding, there are a few are numbered here: automobile, material handling, railroad, shipbuilding, aerospace, chemical, pipeline, manufacturing and machine tools. These are just a few of them. If you look around, you can see welding is there in almost every product, especially metallic product around you. Again, coming back to your table lamp, it has got a spot welded part, right? So most of I would say most of the products, metallic products, has some kind of welding present in them. So let's see the definition. Well, welding is a material joining process which produces coalescence. What do you say, coalescence? Coalescence means fusion or mixing together of materials by heating them to suitable temperatures with or without the application of pressure, or by the application of pressure alone, okay, and with or without the use of filler material. So it is the fusion of materials. Clear? Another important point is welding is used for making permanent joints. But if you go for a nut and bolt, you can say it is not a permanent joint, it is a temporary joint. You can dismantle it, you can use it again, but in case of welding, it is an advantage as well as a disadvantage. Since it is a permanent joint, you cannot dismantle. You can dismantle it, but you may not get the original structure. It is used for automobiles, aircraft, railway wagons, general repair work, shipbuilding. Clear? So that is welding by definition. So let's see, when welding is done without the addition of filler metal to join two metal pieces, the name is autogenous welding. Examples are resistance welding, cold welding, without the addition of filler metal. Without the addition of filler metal. If with a filler metal having the same composition as that of the base metal, so you may be guessing what is this filler metal. Just remember the arc welding which you have seen, which you see around the rod, the welding rod is the filler metal. Okay, so well, the welding with a filler metal is called homogeneous welding. Example is arc welding process. And then another one is with a filler metal with a composition different from that of the base metal. Again, the filler metal is there, but its composition is different from that of the base metal. Base metal is the metal, two metals which you are trying to join together. So that is called the base metal. And if the filler metal has a different composition, it is called heterogeneous welding. Remember, brazing and soldering operations. So this is the outline of the wall joining processes. It's a very interesting diagram, right? You can see a joining process and equipment. Okay. In joining process comes three of them: welding, adhesive bonding, and mechanical fastening. These are the three classification of joining process. As designers, would be required to design welds you'll be required to design joints, mechanical fastenings. Okay, so in welding, again the classification is fusion welding, the brazing and soldering, and solid state welding. And in mechanical fastening, seaming, crimping, stitching. Yeah. Again in fusion welding, if you look under fusion welding, you can see chemical and electrical, right? And in solid state, electrical, chemical, and mechanical. In chemical welding, there are oxy-fuel gas and thermite welding. In electrical welding, arc, resistance, electron beam, and laser beam. In solid state welding, the resistance welding comes under electrical, then diffusion and explosion in chemical, cold, friction, and ultrasonic in mechanical. So this is the broad classification of joining process. So you may, I suggest you to by heart this diagram, not for your academics, but as an engineer, you will need it throughout your life. Comparison of various joining process. So you have seen in the last diagram, you have seen quite a number of process classifications. So how do you compare it? You give a importance of 1, 2, and 3. Very good, good, and poor. If you take arc welding, the strength is very good, design variability is good, small parts is poor, because it is a bit tough to weld small parts using arc welding. Large parts, it is the best process. Tolerance is not so good because you are dealing with a heavy voltage electrode, and it all depends on the workman's skill to get high tolerance levels. Okay, reliability is much good, ease of maintenance is somewhat, visual inspection is okay, cost is again in the middle range. So like this, if you compare different processes, fastening, clear, adhesive bonding, bolts and nuts, you can see a broad comparison. Then, so these are all joining methods. So the choice of joining methods depends on the application, the joint design, the material involved, the shape, thickness, and sizes of components to be joined. So a designer's, an engineer's job is this broadly. As a designer, you will be doing these things. Types, again you have seen the types in the last penultimate slide. Again, it is a broad classification: plastic welding or pressure welding, and fusion welding or non-pressure welding. Okay, in pressure welding, the piece of metals are joined or heated to a plastic state, and they are forced by external pressure. Here they are heated to a molten state and they are joined together, so there is no pressure here. So that is the class. Well, weldability is the easiness with which a sound defect free weld is produced in a metal or an alloy, and the definition goes like this: the weldability of a metal or an alloy depends on certain points: melting point, thermal conductivity, thermal expansion, surface condition, and change in microstructure. So if you melt a low melting point alloy like an aluminum alloy, okay, melting of a large quantity of base metal must be avoided, which means aluminum has a very low melting point, right? So if you don't follow the proper procedure, you may waste a huge quantity of base metal. you may melt away, you may burn off a huge quantity of base metal. Clear? So melting point is a very important factor. Thermal conductivity. Okay. Then here again, alloys with thermal conductivity are difficult to be brought to their fusion points. Why? Because they just transfer away the heat, right? They just gives away the heat from their body very easily. So they cannot retain the heat in them, which affects the fusion point. It is tough to reach the fusion point. More heat has to be supplied, which affects the efficiency of the process. Which means, an example is aluminum. Aluminum needs to be supplied with more heat than steel. You may wonder why. Aluminum, very light metal, right? Low melting point than steel. The common logic says that you will need less heat. But since the thermal conductivity of aluminum is very high, it just transfers away the heat. More heat has to be supplied. The next point is thermal expansion. Yeah, rapid cooling of metals having higher thermal expansion coefficient results in larger residual stresses. Okay, the expansion coefficient is high, which means you heat the metal and it cools very fast, right? The expansion of a joint parts can give rise to residual stresses. The fourth point is surface condition. Surface condition is another issue. Dirty surface will lead to porosity. Porosity is what? Porosity is blowholes, or porosity are voids or spaces, empty spaces, empty bubbles inside the joints. So this dirty surface will lead to porosity. Okay. Then another one is change in microstructure. Clear? So weldability depends on change in microstructure. We know that during welding, metal is heated, and if you go by the basic material science concepts, when you heat a metal to its melting point, it can change the microstructure and ultimately the property of the material. So you can say weldability depends on change in microstructure. Then the weldability of metal can be changed by modifying its physical, chemical, thermal, or metallurgical properties using proper welding procedures, shielding atmospheres, fluxes, filler metal, and pre and post weld heat treatments. Okay, welding procedures. Okay, so welding procedure two metal joints, how do you weld them together? There are certain requirements. You cannot just simply put together two metals and weld them. There is a procedure for every metal. There is a procedure for every structure. There is a procedure for every design. Then shielding atmospheres, fluxes, filler metal, and heat treatments, like metals with thermal conductivity, varying thermal conductivity, or thermal expansion need to be treated before welding and after welding, which we will see in detail later. So let's see some of the weldability of some of the metals. Plain carbon steel. Okay. So these are the weldability of some of the metals. Okay. Well, as a designer, what should you be looking into when you design a welding or a welded joint? Okay. The heating the base metals to be welded to higher temperatures to produce a weld joint result in their metallurgical and physical characteristics. As I said in the last slide, it affects the properties or the characteristics of the metal, whether it is physical, microstructural, chemical characteristics, right? The rate of heat input and the thermal properties of the base metals decide the magnitude and distribution of temperatures. Okay, as an engineer, you must look into this part. The rate of heat input and thermal properties. It decide the distribution of temperature in the joint. This temperature distribution affects the microstructure of base material. As I said in the last slide again, it affects the microstructure of the base materials. And these resulting microstructure control the strength, ductility and toughness of the welded joint. Some parameters. It can affect more parameters of the welded joint, but generally speaking, it affects the strength, ductility and toughness of the welded joint. Because why? The microstructure has changed. So the designer should have knowledge of effect of localized heating on the microstructural changes in the material, the effect of residual stresses or locked up stresses as a result of uneven heating. Why? What do you mean by uneven heating? Because when you join two sheets, you are heating just the edges of the sheet. You don't heat the wall area of the sheet. So it gives rise to localized heating or uneven heating and cooling of the metal. So it can give rise to uneven stresses, residual stresses in the product. Welded component has poor fatigue and impact properties than correctly designed castings and forging. This is negative characteristic of a welded joint. They have poor fatigue and impact properties than correctly designed castings and forgings. So let's see the process in detail. So this is the welding electrode. This is the weld pool. When you join two metals, here you can see it here, one metal and the other metal, the second metal, right? You are welding it. Okay, so you pass the welding electrode. You start from one end, you pass the welding electrode from that end. It is moving like this, and you can see the excuse me, weld zone here. Clear? So this is the heat source. Okay, it can be anything. It can be a flame if it is an oxyacetylene welding. It can be an arc if it is an arc welding, or a laser beam or electron beam in those kind of high energy weldings. So the fusion zone is here, the heat affected zone, and a liquid weld pool. So this is the weld pool. You mean you know what is a pool, right? A pool, right? So it is a pool of molten metal. Clear? During welding, arc or fusion, the weld joint experiences a thermal cycling. This joint experiences a thermal cycling, right? Material is heated rapidly and cooled at a slow rate. Because why? Because you are putting heat through an electrode, so it is heated rapidly, and cooling takes place slowly. Maximum temperature exceeds melting points, and locally a weld pool is formed. So this is the weld pool. Okay, during cooling, the molten metal solidifies, forming weld joint. Clear? So the solidified metal, you can see here the solidified metal. The weld pool has cooled down. This is the weld pool. Here it has cooled down. Here the fusion of coalescence of two metals are achieved here, right, in the weld pool, and it suddenly cools down to form the solidified metal. So adjacent to the metal weld pool, metal reaches varying temperatures. So you can see the different color schemes here. So it is the it depends on the varying temperature zones, temperature gradients. Okay, it depends on the distance from the fusion boundary. So this is the fusion zone. So different temperature zones are present in a weld metal joint. Then, as I said, the weld metal joint experiences temperature cycle, and this temperature cycle influences the structure and properties of weld strongly. So see, these are the two metal sheets which are to be joined. This is the front view, okay, and this is the top view. Two metals. This is the welding direction. The arrow gives the welding direction. You start from here, you move like this. It's the welding direction. You can see the isotherms at the plate surface. So this is the weld pool, and these are different. This oval, the oval shapes are all different temperature zones. Okay. So it experiences this is the temperature isotherm in the temperature position graph. Right here, the temperature reaches the maximum at the weld pool. Okay, and when the metal cools down, you can see the temperature dropping down. So the leading edge of the temperature pattern is compressed. Okay, arc move towards cold metal continuously. Here ahead is a cold zone. Okay, cold zone. So the arc is moving towards a cold zone. That is why it has got the leading edge of the temperature pattern is compressed. It is not sharp because it is moving towards, continuously moving towards a cold zone. That is why the temperature pattern is like this. The trailing edge becomes extended. Trailing edge becomes extended. Okay, because the arc leaves heated metal behind. This is the pool, and these are all different temperature zones which are still hotter than the surrounding metal.